Good day again, learners. It's me again. For those who were not here last week, I'm Malankamo Tloiwa. We are continuing with trigonometry because it has many facets. Last week we dealt with double angles. In other words, one composite angle made up of two angles. We'll meet them in some guys today. But today we are looking at the application of the rules: sine rule, cosine rule, sine rule, cosine rule, and area rule. And we are looking at 3 dimensions. What you are looking at, that paper you are looking at, is 2-dimensional. It has only length and breadth. 3-dimension would also include height or thickness or depth. And that is what we'll be looking at. You will notice that we almost always have 2 triangles. One of them is right-angled. The other one is non-right-angled. This is where the rules come in, especially the sine rule. Now if you look at the diagram that we have in front of us here, it is said that from point A, the angle of depression to B is x. And the angle of depression from the same B is C. From B, the angle of depression to C is W. Now, the x you see that I've written here, comes from the fact that this line is parallel to that line. Look at the Z, which is what you must do when you get a diagram. Complete the sides and the angles using your axioms and your theorems. Now this stopped here. But let's first look at the first question. It says, write ACB, angle ACB, in terms of W and Y. Now let's look at the angles. You are not given this angle here. You are given this one. Okay? But if you continue with this triangle here, you will realize that you have the Z here. This is Y. This will be Y. This angle there will be Y. But at the same time, vertically opposite angles are equal. Then you have Y. So in this triangle, this, that, then you have your Y and you have your W. And use your knowledge of angles of a triangle. That ACB, the one we want to write in terms of the others, plus W plus Y will give you 180, from which ACB equals 180 minus W plus Y. That answers your question. There is a reason why they have given you this, because you are going to need it when you solve this. RTP stands for required to prove. What do they want us to prove? That AC, this side here, is equal to AB sine W plus X over sine Y plus W. In the same way that you did not have Y here, but you had to use your knowledge of parallel lines to get Y here, then here, you also use the same knowledge to get X here, because this X and this angle are alternate angles. And now, in this triangle ACB, which is non-right angled, you need to involve AB. Why? Because it forms part of what you need to prove. So it's AB over. Now, let's clarify one thing about opposite. What do you mean when we say a side is opposite another? If this angle is theta here, okay, the easier way of remembering which side is opposite to theta, it is made up of this arm and that arm. This third side, which is not part of this angle, is opposite to the side. If you had alpha here, this part is part of this angle and it is adjacent. It is opposite theta but adjacent to alpha. So you have AB, it will be opposite. It is not part of ACB, so it will be opposite ACB. But ACB is equal to 180 minus W plus Y. So it is AB over the sine of, maybe we should write it down here. Where does all this come from? It is actually AB over the sine of 180 minus W plus Y. Right? But the sine of 180 minus theta is equal to the sine of theta. That is why when we come back here, you find that it is AB over the sine of Y plus W. It is actually AB over the sine of 180 minus W plus Y. But this is the same as the sine of W plus Y. I need to emphasize that 180 minus W plus Y is not equal to W plus Y. It is only their signs that are equal. So you involved AB here over the side opposite it. And you must involve AC. Why? Because we are looking for AC here. There's nothing really difficult when it comes to the choice of sides and angles. But what is AC opposite to? It is opposite to, you see it does not form part, it does not form part of this ABC. So it must be opposite to ABC. But ABC is equal to W plus X. And so you can make AC the subject of the formula. If this confuses you, you can first cross multiply, where you will get your AB sine W plus X. And this one will be multiplied by sine Y plus W, but then divide by sine Y plus W, which is what we were required to prove. This is what we were required to prove. When you look at the second diagram, you are required to prove that PQ is equal to Q sine Y tan Z over sine X. Now things may look strange to you because this is three-dimensional. This is said to be 90, it makes sense to you, but this is also 90. That's because PQ from this vertical plane is perpendicular to the plane QRS, and there's an axiom that says a line which is perpendicular to a plane is perpendicular to every line or line segment on that plane. So since it is perpendicular to QRS, it must be perpendicular to QR, which is a line on the plane. Now, it brings me to the point that I want to indicate. I know you may find in certain books that we use the sine rule in this triangle and also the sine rule in this one. But my take is, if it is right angled, there is no need really for the rules, because the rules are meant to help us when the triangle is non-right angled. Another thing, look at this. PQ equal to Q sine Y tan Z over sine X. How many angles are we talking about? we are talking about x, y, we are talking about x, and we are talking about z. So what I suggest you do, although methods differ, is that you look at x. This x is in a non-right angled triangle. You look at y. This y is in a non-right angled triangle. However, when you look at z, this is in a right angled triangle. So directly, immediately look for tan z. Immediately look for tan z. We look at tan z, okay, because the angle z is in a right angled triangle. Therefore, tan z is opposite over hypotenuse. In this case, your hypotenuse will be opposite the right angle. That's why it is PQ opposite over the right angle. Or rather, not over hypotenuse. Tan is opposite over adjacent. So it is PQ over QR. From which you make PQ the subject of the formula. Why do you make it the subject of the formula? What you ultimately have to prove has PQ on the left-hand side. So you put it on the left-hand side where it belongs. You have QR tan Z. Now, what we are talking about here, the y and the x, are not in this triangle. So we need to come back to this triangle. We must involve this QR. One, it is what we call the link, because it links PRQ and RQS. When you get to the right angled triangle, you then apply the sine rule, and QR must be one of the sides you use. What is the angle opposite it? It is this one. That's why you have QR over sine Y is equal to, again, you don't just choose any. Why don't I choose RS? Because there is no RS here. Why do I choose A? You are directed by what you have to prove. So you go to A, and the angle opposite it is this X. That's why you have A over sine X. And then we make QR the subject of the formula. Why do we make it the subject of the formula? I will explain to you in a short while. When you do that, you get A sine Y over sine X. So you go back to when we say PQ is equal to QR tan Z, and instead of QR, you put A sine Y sine X, which is what you were required to prove. It is easier, actually, than you think. Let us look at another example. You are required to prove that H, that height there, it's not drawn properly, is equal to d sine x sine z over sine x plus y. Notice that when we were here, in the tan we involved PQ. Why? Because we had it here. In the same way here, we must involve H somehow. And the same reasoning holds. Why did I look for sine x? You look at this triangle. Sine x is equal to H over AT. Opposite over hypotenuse. And we make AT, H rather, the subject of the formula. And then we have in this other triangle, okay? This once again, look at this, is a plane. This H is perpendicular to the plane, Therefore, it must be perpendicular to this line. Therefore, this triangle here is right angled. Okay? And this then becomes your hypotenuse in this triangle. In this triangle. So the sine of x is opposite, which is h, over hypotenuse, which is 80. But we want to write everything in terms of h. That is why we then make h here the subject of the formula. So h is equal to 80 sine x. Once again, look at this 80. It is part of this triangle that I started with. It is part of this triangle. But it is also part of this triangle. Hence, we go to the non-right angle triangle, and we have 80 over sine z. Here's your z. 80 is opposite to z. Okay? Is equal to d. Now, why do we use d? Remember, it is part of what we need to prove. You don't just write them. And d is opposite bt. So, but what is bt? Where do I get z from? From the calculation here, that this is 180 minus z plus y. It is said that this is, if I may draw it aside, it is the triangle is like this. Then you get this, and then you get that. Okay? And this is your y. And this is your z. And your trig ratios say this must be equal to 180 minus y plus z. That's where I get that magnitude from 180 minus z plus y. Here I indicated it correctly. First, I didn't just go straight to sine z plus y. I indicated it as sine 180 minus z plus y. From which, if you cross multiply, I tried to be systematic here. If you cross multiply, then we have 80 sine 180 minus z plus y is equal to d sine z. But, like I indicated here, the sine of 180 minus theta is equal to the sine of theta. The sine of 180 minus w plus y is equal to the sine of w plus y. Similarly here, the sine of 180 minus z plus y is the same as the sine of z plus y. Is equal to d sine z. Therefore, making 80 the subject of the formula, 80 is equal to d sine z over sine z plus y. And therefore, you go back here. You said h is equal to 80 sine x. Here's sine x. But the 80 is not there. That's why we had to eliminate it. Now, if we may go back. I want us to concentrate on this. Hey, your pens. On this QR and this 80 here. You will notice that they came into the picture somehow. and we had to eliminate them. Why? Because if you look here, they are not part of what we are looking for. Similarly, 80 came into the picture here, but we had to eliminate it because it is not part of what we are looking for. How did we manage that? Let me tell you a little story. There is this stokvel of 18 people. At the end of every year, they go out to have some fun, to enjoy their money. But since they always go to a faraway place, the biggest challenge is transport. But they never worry about that. You see, this is what they do. They always invite Peter. Now, two advantages. Peter is impressed or flattered by the invitation itself. Secondly, they tell Peter that while we are each going to pay 90 rands, you pay absolutely nothing because we love you to bits. Peter goes there, stolen-headed and happy. But wait a minute. Why do they invite Peter in the first place? You see, Peter happens to have this E20, 20-seater mini bus. He goes there and happily carries these people in his E20. They go to this place of fun, have fun, and they come back. Problem solved. Problem solved. Now, mathematicians do the same thing. Okay? You always have this link, this thing that I call a link, and it always appears, but somehow you have to get rid of it. If you were to tell it to go away because it is not part of the final formula, it would simply dig its heels in and refuse. But mathematicians do it this way. They make it feel important. How do they make it feel important? They make it the subject of the formula. And once it is the subject of the formula, it gladly goes away. Okay. Once QR or 80 is the subject of the formula, it gladly goes away. That's how mathematicians could do this. Now let's recapitulate. You always have, almost always, a right-angled triangle and a non-right-angled triangle. I prefer to look at the angles and work first in the right-angled triangle and then make what I'm looking for the subject of the formula. And then there is this side that is the link. I also use it in the non-right-angled triangle, especially when I do the sine rule, and then eliminate it, like I indicated, make it feel important by making it the subject of the formula. Let's deviate a little. I indicated last time that people often say, you ask them what is the sine of an angle, sine of an angle. Let me put theta here. And people invariably say, now if we have a circle of radius r, and obviously this will be the y value, and this will be the x value. People will then say sine of theta is equal to y over r. The cosine of theta is equal to x over r. The tan of theta is equal to y over x. But this, people, is not the definition of any of these ratios. A simple illustration would suffice. I indicated last week that this is the Cartesian coordinate axis, the x-axis, and this is the y-axis. Right, but we are not done. We must also have a circle of radius r. And we are still not done. The final thing, this angle here must be in what we call standard position. When is it in standard position? When the initial arm is here. And it is centered here at the origin of the Cartesian plane. A simple thing to indicate that you don't just say the sine of any angle is y over r is if we have an angle here. Let's call it alpha. Would you say this is y over r? Of course, y over r would mean adjacent over hypotenuse, which is the cosine and not the sine. And all the others would actually be wrong. Would you say the cosine is x over r? No, x over r is opposite this. It will be the sine rule. Now, you don't have to be confused. If I say, on the one hand, we say it is y over r. On the other, we say it is x over r. That's because this y over r is just a special situation. When we are on the Cartesian plane, number 1, when we have a circle of radius r, number 2, and when the angle is in standard position. For instance, if I chose my circle to be w, then we would have y over w and not y over r, x over w and not x over w. And if I'm looking for the tan of alpha, then we have a completely different situation, not y over x, but x over y. So please get that clear. The definition of these is what you know, opposite over hypotenuse. This one, adjacent over hypotenuse. And this one here, opposite over adjacent. Now it will not make any difference even if your triangle is facing this way. That will not make any difference. If your beta is here, then your cos is not this over that. Okay, let's call it A, B, C, with the side A, the side B, and the side C. You see, first of all, you don't have x, you don't have y, you don't have r. Does it mean you cannot find the cosine or the sine or the tangent? Of course you can, because the cosine would then be adjacent. Now, which side is adjacent? This side, together with the hypotenuse, forms this angle. This side that together with the hypotenuse forms the angle is adjacent. And this one, like I said, which does not form any part of beta. Remember, AB is one arm, BC is another. AC or B does not form part, then it would be opposite. But another thing that we need to indicate is that there is no such thing as opposite on its own hanging like that. For instance, if I ask you in your street which house is opposite, the question is incomplete. I must say opposite with reference to what? For instance, if your house is here, and this is your street, or rather this is your street, and there's another house here, that side of the street, this will be opposite your street. But if there's a house here, it will still be diagonally opposite you, but it will be adjacent to this one. In other words, this house on its own is neither opposite nor adjacent. It depends on what angle you are talking about. Like I've just said, AB is adjacent. Adjacent to what? To the angle B. But what is it with reference to angle C, or let's call it angle alpha? With reference to angle alpha, you will see it is opposite. So we need to do that. When we say adjacent, it is actually the angle adjacent to the angle we are talking about. When we say opposite, it is opposite to the angle we are talking about. So be careful about that. So these three-dimensional problems are not difficult. You have first a right-angled triangle, and then you have a non-right-angled triangle. In the right-angled triangle, we use the definitions, the very definitions I'm talking about. Opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. But in a non-right-angled triangle, we often, most of the time, use the sine rule. When do we use the cosine rule? Two conditions. If you have two sides, and an included angle. But also if you have squares and or square roots, then you know that I must use the cosine rule. Similarly with the area rule. If this is 3 centimeter and this is 4 centimeter, you don't even need this angle here, because the area here would be half base times height, which is half 3 centimeter times 4 centimeter, which is 6 centimeter squared. However, suppose this PQR is not right angled, then we use the area rule, which can also apply here, that says area is equal to half the product of the two sides times the sine. The sine of what? The sine of the included angle. And again, another thing, the easy thing to remember is that the so-called included angle is very simple. It is the angle made up by the very sides we are talking about. This PQR, which in this case happens to be 90, is the included angle between 3 centimeter and 4 centimeter, because one arm of this angle is PQ, the other one is QR. So it will be the sine of 90. Now, you have half times 3 times 4 is 12 centimeter squared times 1, because the sine of 90 degrees is 1. You still have your 6 centimeter squared. It is unnecessary to use this one when the triangle is right angled. But suppose this was 60, then you don't have a choice, because you can't use half base times height. Perpendicular height necessarily means that this and that must be perpendicular to each other. In other words, it means that PQ must be perpendicular to QR in order for you to use the area rule, or rather the area of a triangle in the form half base times height. So normally when you have a right angled triangle, there's no problem with finding the sine, there's no problem with finding the cos, there's no problem with finding the tan. There is also no problem with finding the area. It is when the triangle is not right angled that we resort to our knowledge of the rules, the sine rule, the cosine rule, and the area rule. Let us look at the rules. I did not derive them because the assumption is if we are doing this section, they must have been treated already. If you have not treated them, I will not derive them, but I will simply write them down and explain what it's all about. Let's start with the sine rule. In any triangle, consider triangle ABC. Any triangle. Let's make it acute. You can put A anywhere, B anywhere, and C anywhere. The convention in mathematics is to choose the side opposite the angle to have a small letter, the same as that of the angle at the vertex. So this would be A, this would be C, and this would be B. Now obviously you cannot say opposite over hypotenuse. For instance, to start with, hypotenuse is strictly that side which is opposite a right angle. So if the right angle is not there, you cannot use the sine definition. But what does the sine rule say? It says choose any angle. Let's choose A. Determine its sine. Put it over the side opposite that angle. It is equal to, in the triangle, the sine of any angle that you prefer to choose divided by by the side opposite it. And finally, we can have this. This is the sine rule. But the beauty of it is that at any given time, we use any two of them. We use this one, or we use this one, or we use that one. But what do you notice? You have 1, 2, 3, 4 variables. So, 2 angles, 2 sides. In order to solve using the sine rule, you must have 2 of the same kind and 1 of the other. If you have 2 angles, let's suppose you are looking for B. You'll have 2 angles, and the side that is given must be opposite one of the angles. Let's suppose it's A that you don't know. The 2 sides A and B are given, and the angle B is given. The other angle that the other angle that is, or other side that is, the side that is given, or rather the angle, because we have 2 sides and an angle. The angle, this angle here, must be opposite one of the given sides. So with the sine, we use 2 of an angle, 2 sides, and 2 angles and side opposite. Let's call this angle 1, angle 2. Either angle 1 or angle 2. Similarly, if it is 2 sides, we have either side 1, side 2, and an angle must be opposite either side 1 or side 2. It has just been indicated that I have only 5 minutes. So it's less than that. Now, that is what the sine rule is said. So you must be having 2 of an 2 sides and a side, 2 angles and a side opposite one of the angles, or 2 sides and an angle opposite one of the. Then you can use the sine rule. What about the cosine? I'll use the same triangle. I'll use the same triangle. They say choose any side. Let's choose B. Take its square. It is equal to the sum. After taking B, you are left with A and C. It is equal to the sum of this. Does this look familiar to you? Yes, the theorem of Pythagoras. Only 1, this triangle is not right angled. 2, we are not done. Minus twice these 2 sides, but not squared this time, the product of these 2 sides, times the cosine of the included angle. Now, like I said, the included angle is nothing except the angle made up by the very sides A, B, B, C, which is C and A. So it is the cosine of B. Now, this applies to any other side. A squared equals B squared plus C squared minus 2BC, the cos of A. And finally, C squared equals A squared plus B squared minus 2AB times the cos of C. And like I said, you will notice that there's a square here. So if your problem has a square or a square root, that tells you that here I'm called upon to use the cosine rule. This is what we've been applying. I've been applying them without going over them because the assumption is that you have already treated the section. And finally, I don't know if you'll be able to do the area rule, a problem that has the area rule today. But what does the area rule say? I've already indicated. Again, I choose a non-right angle triangle. Let's call it PQR. And I have small p, small r, and small q. The area of this triangle, PQR, is then given by a half any two sides. So let's choose PR times the sine. Note it is not the cosine this time, the sine of the included angle, and in this case it is Q. Now what directs you to use P or R? It is if both P and R are given, or we are looking for R and P is given. In other words, you are directed by the given information as to which two sides you take. So it is, if you are not given P and R, but P and Q, then you would have half PQ. But now the angle made up by P and Q is R. This would be the included angle. And you come here, and finally you could have been given Q and R, then you have half QR sine P. By the way, convince yourself that this is correct. By doing what? By first, if you have the three sides and all the angles, determining it using P and R and the sine of Q, getting a magnitude, determine it using P and Q and the sine of R, get the value, determine it using Q and R and the sine of P, and you'll find that you get the same value every single time. That, in a nutshell, is what we mean by the sine rules. Notice that I chose a non-right angled triangle. You don't need these things. You don't need the area rule. You don't need the sine rule. You don't need the cosine rule if we are having a right angled triangle. For the sine and the cos and the tan, you use the definitions of sine, the definition of cosine, and the definition of tan. For the area, you use the fact that two of those sides are perpendicular to each other, so you use half base times height. I'm sure my time is running out now. Let's recap. Let me put back this thing, because not three-dimensional as such, but the application of the sine and the cosine give children a problem. This was given like this without the x here. And what you use is your knowledge that when two parallel lines are cut by a transversal, these axioms must be at your fingertips. When two parallel lines are cut by a transversal, A, B, C, D, E, F, G, H. Then the alternate angles are equal. Now which ones are alternate here? You have H, and E. Notice that they form a Z. That's how you'll recognize them. And F, as well as F and B. Notice that they form an F. It looks funny, but it is still Z. Alternate angles are equal. Corresponding angles are equal. You have A and B. Now, if you take it down here, here's your A, here's your B. These are corresponding angles. What do you see here? You see an F. They form an F. This side too, you have a G and an E. And if you look at this, you have an F. Yes, it's facing this way, but it is still an F. You need to be able to recognize these. And finally, although we seldom use that, you have co-interior angles are supplementary. Now, how will you recognize, apart from the F, corresponding angles? This line here is called the transversal transversal. Corresponding angles are on the same side of the transversal. A is to the right, so is B. A and B are corresponding, they are to the right. At the same time, if this line is AB or KL, A is above KL, B is above MN. In other words, they are on the same side of their respective angles. On the same side of the transversal and on the same side of their respective angles. Similarly, when you come this way, F is to the left of the transversal, D is to the left of the transversal, F is below KL, so is MN below, D below MN. So for alternate angles, they do the opposite. When one is on the right, the other one is on the left of the transversal. When one is above its line, the other one is below its line. The alternate angles. If this is to the left of the transversal, the B which alternates with it is to the right, and since this is below its line, this one is above its line. You should have these things at your fingertips so that you are able to identify which are corresponding, which are alternate, and which are co-interior. Then you won't have a problem dealing with them. If I may bring back what we started with, this angle here was not given, but we know that this is parallel to that. It forms a Z, and therefore this must be X. Remember, when you come here, we are talking about W plus X, and yet I see only W, and there's X up there. I use the fact that alternate angles, when the lines are parallel, are equal. The same thing applies to the W plus Y there. I have only W here, but there's the Y there. How do I get it here? Again, it was not even necessary for us to have used the alternate angle first. In other words, this angle is equal to that angle. We could have stopped here because there's your F. Okay? This angle corresponds with this one. So if this is Y, this must also be Y. Now I want to recapitulate by saying, when you deal with these problems, especially 3D, that require you to apply the rules, it is not only the rules that are applied, but also your knowledge of parallel lines. When two parallel lines are cut by a transversal, corresponding angles are equal, alternate angles are equal, co-interior angles are equal, which is what you have applied here. Not only that, you have also applied the fact that the sum of angles in a triangle is 180 degrees. And you also apply your cast rule. Also apply when you have theta here, let's say 30 degrees. If you move this way and you have the same theta here, 30 degrees, the sine of this, now this will be 180 minus 30, which is 150 degrees. The sine of 150 degrees is equal to the sine of 30. If we call theta, we generalize it to, say, theta, then how do we get it? It is 180 minus theta. In the same way that 150 is 180 minus 30. And I wish to reiterate that you often come across the situation where you are dealing with sine of 180 minus, say, alpha plus theta, which then is equal to the sine of alpha plus theta. But like I indicated, it does not mean 180 minus alpha plus theta is equal to alpha plus theta, in the same way that 30 degrees is not equal to 150 degrees. If it were live, I would take questions. Let me remove this and have this from the textbook. That this is the horizontal plane. These are vertical planes. This is a vertical plane. This is a vertical plane. And this one is an inclined plane. We're going to take a short commercial break. And when we come back, we'll continue. We are going to take a short commercial break, and when we come back, we will continue. Welcome back. Let's look at, this was taken from a book. You have that two planes, one horizontal, one vertical. And if you read that, it says in the figure alongside, A, B, and C are 3 points in the same horizontal plane. AD represents a lamp pole that is perpendicular. And this is the lamp pole that is perpendicular to the horizontal plane. Given BDA equals theta, and BCA equals beta. BC, which is this length here, equal to x. Write BAC in terms of theta and beta. Now, first of all, where do you find BAC? Find it in this triangle. And where do you find theta? In this one. And in this one. So what do you know about this BAC? This theta and this beta. That when you add them all together, they give you 180 degrees. This is where they get A equal to 180, BAC. They've written A here, but it's actually BAC. BAC. It's equal to 180 minus theta plus beta, angles of a triangle. And then it is said, show that AB equal to x sine beta over x sine beta over sine theta plus beta. Now look at AB. What do you notice about it? It is part of this triangle. It is also part of this triangle. It is what we call what? The link, which means you're going to use it here, and you'll come back and use it here. Now you have sine A over A is equal to sine B over B. Which one would be B? In this case, B would be this side here. It is equal to sine C over C. If this is C, your small c will be this one. And, like I said, you only use 2 at a time. Why do they end up with this one? Why have they left out AC? Because in this one, we don't need side AC. So we use sine 180 minus theta plus beta. That is why they wanted you to find it out first. Over x, yx, because x is opposite this angle, is equal to, and you must involve x because x is here, over the sine of theta, or rather the sine of beta, over AB. Why AB? Because actually we're going to need it here. So the choice of sides is determined, but what it is you have to either calculate or prove. So you have to involve x and this, because it is in what we are proving. You also have to involve AB, and obviously if you involve AB, you must involve this angle here. It is 180 minus theta plus over sine beta over AB. And then, there we go again. Why do we have sine 180 minus theta plus beta? But here sine theta plus beta. That is because sine 180 minus angle is equal to simply the sine of that angle. I think they have even used it here. They have indicated it here. Sine 180 minus angle, whatever the angle is equal to the sine of angle. Remember, we're dealing with compound angles. This is an angle, all right. This is an angle, all right. But this theta plus beta, when it is within brackets, it is also an angle. It is what we call a compound. That's why we have changed this to this one. And now you have AB, when you cross multiply, sine theta plus beta equal to x sine beta. And then why do we make AB the subject of the formula? Because this is what we are required to prove. Once again, that's number B. Now AB equal to AC. Show that AB equal to x over 2 cos theta. Show that AB equal to 2 cos theta. Let's look at it from this. Let's have this here. Yeah, required in number B, if AB equals AC, show that one, AB is equal to x over 2 cos theta. Now, solution. In any triangle, angles opposite equal sides are equal to each other, and sides opposite equal angles are equal to each other. So if AB is equal to AC, then angle B must be equal to angle C. Let me bring it back here. If AB is equal to AC, AC is opposite B, which is theta, and AB is opposite C, then it means that B must be equal to C. AB is equal to x sine B over sine theta plus B. Now, theta plus theta equal to 2 theta, so you have sine 2 theta. Last week we dealt with double angles, and the double angles say sine of 2 theta equals 2 sine theta cos theta, but in this case our angle is, yes, it's theta. So it is 2 sine, or rather it is sine 2 theta, 2 sine theta, cos theta. Therefore, AB is equal to the sine beta. Rather, on top here we have x sine theta, not x sine beta, x sine theta. So the sine theta cancels the sine theta, and you have x over 2 cos theta. Note that when you used this, whatever you have proved, you can always prove using subsequent calculations. This you proved, so you can use in subsequent calculations. That was number 1 of question C. Number 2 says, prove that AD is equal to x over 2 sine theta. We look to triangle ABD. Triangle ABD. It would help if you had quickly drawn this, or maybe I should quickly redraw it. Theta D B theta A X beta and C. In triangle ABD, this triangle here, we are in triangle ABD. Sine A over A, which is BD, is equal to sine B over small b, which is AD in this case, is equal to sine D over small d, which is sine D is opposite AB over AB. Sine A, which is here, over this side, which is opposite it, and sine B, which is here, over the side, which is opposite it, is equal to sine D over the side, which is opposite it. But the angle A is 90 degrees, so you have the sine of 90 degrees over dB is equal to, why do we say sine B 90 minus theta? That's because since this is 90 and the sum of angles in a triangle is 180, these two together must give you 90. B and theta must together give you 90 degrees, from which B will then be 90 minus theta. So it is the sine of 90 minus theta over 80 is equal to the sine of theta, which is this one, over AB, which is this one. Then we choose, like I said, we go to sine theta over AB. Why do we not include this? Remember, AB is what I call, or what is called rather, the link. It has to be there. Besides, we know it's into. So we choose sine 90 over dB sine theta over AB. Over AD, or rather we choose this one. Sine 90 minus theta over 80 is equal to sine B over AB. But we did it last time that sine and cosine are co-ratios. Their angles must be complements if they are to be equal. So the sine of 90 minus theta is equal to the cosine of theta over AD. That is equal to the sine of theta over AB. We are not done. When we are here, before I use another slide, we cross multiply, and this gives us AB cos theta equals AD sine theta. And if we divide both sides by sine theta, then we have AB cos theta over sine theta is equal to 80. But let's go back. We were required to prove and we did prove that AB is equal to x over 2 cos theta. So we substitute it here. Instead of AB, we have x over 2 cos theta, but we still have to multiply it by cos theta. And all this is divided by sine theta. This is equal to AD. Now this one goes, and you have AD as required. equal to x over 2 sine theta. If I may remove the confusion that might appear here, let's write this here as x over 2 cos theta divided by sine theta. And then we flip and times. So this is 1 over sine. And this cancels. You have x over 2. Now we can see that the 2 and the sine are on the same side. X times 1 is x. And 2 times sine theta is 2 sin theta. It's 2 sin theta. That's about all. Do please take down these and attempt them at leisure. In the following sketch, ABCD is in a horizontal plane. This one. ABCD is A is directly above B. AB is a vertical line. AB equals H. BC equals X. CD also equals X. BAD equals alpha, and BCD equals theta. Show that BD squared is equal to 2x squared 1 minus cos theta. Now, a hint. What does this as well as this suggest to you? What does it suggest to you? I can only give you hints. First of all, this is H. The angle here is alpha. This is A. This is B. This is X. The angle here is theta. This is C. This is X. And this is D. What are we required to prove? We are required to show that BD squared is equal to 2x squared into 1 minus cos theta. this suggest to you? This is a square. This is a square. Two things should suggest to you two things. One, you are having a square. And two, the triangle is non-right angled. These two facts suggest to you that you must use the rules. Number one. Number two, which specific rule? The cosine rule. I said at the beginning, the square and the square root will immediately suggest to you what course of action to take. At any rate, the question itself is already written in terms of BD squared, so you don't have a choice, but the square, like I indicated, together with the fact that it's non-right angled, suggests that we can't use the definitions of sine, cos, and tan, but it also suggests that because there's a square, the one rule that involves the square is the cosine rule. And that is what then you proceed to use. BD squared will then be equal to, remember it is this side, it must be equal to the other two sides. X squared plus x squared. I'm skipping the BC and the CD story so that we can move fast. Okay? Is the square of the other sides minus twice times the cosine of theta. But what do you have here? This is 2x squared minus, what do you have? X times x. It is again 2x squared times the cosine of theta. What does your mathematics say? What does your mathematics say? I have two terms. This is one term. This is the other term. But in this one term, there's 2x squared. Also here, there is 2x squared. So we take the 2x squared out. And we are left with here with 1, here with cos theta. It might have looked formidable to you. It might have looked completely difficult. But like I said, when you are in this, if the triangle is non-right angled, first of all we use the rules. And normally we use the sine rule. But if you have a square or a square root, then you know that you must use the cosine rule. So in this case, it is this side squared equal to this side squared plus this side squared. Minus twice this side times this side times the cosine between them, which is the cosine of theta. And when you simplify it, you notice that 2x squared is common. So you take it out and you are left with 1 minus cos theta. I think we've run out of time. But before we part, it is an open secret. It is an open secret that the Department of Free State, or rather Free State beat all the other 8 provinces last year with matriculation results. It baffled me because it had never happened before. So I did research, I phoned around, I visited libraries, I Googled, and guess what? I found the secret. And I'm going to give you that secret. They'll probably fire me for telling you that. And if they do, it's your fault. But I'll tell you all the same. They worked harder than everybody else. If you want to outperform anybody, you must outwork them. There's no circumventing that. I wish the audience, you were here as an audience, so that you could ask me questions. However, I hope you took down what I ask you to take down. Or let me leave this one here for you to take down, because sometimes when one speaks, you want to concentrate, but at the same time, you want to write down. Let me go to the question. The question says, show BD squared equal to 2x squared. And let me repeat, a square, together with the fact that the triangle is non-right angled, gives us two things. The non-right angles tell us we must use rules, because we can't use definitions of sine, cos, and tan. And the square, or the square root, tells us that you must use the cosine rule, which is what we applied here. And the cosine rule, if we understand it, says you take any side, in this case BD squared, take the square of that, it is equal to the sum of the squares of the others. In other words, BC squared plus CD squared, which happen to be x, both of them, minus twice those sides, not squared, the product of those sides, times again the product of those two sides together with the cosine of the included angle. And like I indicated, it's easy to identify an included angle. It is actually an angle made up by the very sides. So BC and CD make up theta. So the included angle between BC and CD is theta. So you use the cosine here. From here is simple algebra. X squared plus x squared is 2x squared. X times x is again x squared. Again, simple algebra. When you have terms joined by plus or minus, then you don't have one term but an expression. So this expression here consists of two terms, 2x squared together with minus 2x squared cos theta. But in these, 2x squared is common. That is why we take it out. And you may wonder why we have 1 here. You were actually doing this. You are actually multiplying by 2x squared divided by 2x squared, which is 1. And you know 1 is the identity element of multiplication. It does not change anything. So if I took the 2x squared here, I also divided. That is why I was left with 1 here. And when I divide by 2x squared here, I'm left with cos theta. So whatever question may appear to you to be formidable, please note, if it is right angled, don't bother with the rules, sine rule, cosine rule, area rule. Just use the definitions of sine, tan, and cos. And also with the area, just use the fact that the area of a triangle is half base times height, because you do have the height and the base. But if it is non-right angled, then use the sine rule under normal circumstances. But if you have a square or a square root, and the triangle is non-right angle, that suggests that you use the cosine rule. And you need to know what the sine rule says, what the cosine rule says, what the area rule says, in order to be able to apply it. If time permitted, we would then go to a question that requires us to use the area rule. But anyway, I'm sure you get the picture. It was nice presenting to you. Hope we'll meet again in future. God bless you.